Now that we have an idea on some basic machine learning methodologies, we go back to our credit default dataset. The objective using this dataset is to predict if a customer will default on his payment or not. Using such an information, the bank or the financial institution can help construct some kind of customer profile and also review its decisions to continue using the credit card or giving credit card to a customer, or decide on the nature of the loans to be executed to a particular customer whose historic credit card behavior is known to us. Using our newly acquired machine learning terminologies, we can see that this problem can be viewed as a classification task. The response variable is the column default payment next month, which takes on two values, 0 and 1. So this problem is a binary classification. The data also has 23 features, excluding the ID variable. Remember that it is just an identifier for customer and not meaningful or informative in any other way. We do not expect that the ID of a customer will contain any information about the credit card behavior of the customer. We had a brief introduction to scikit-learn earlier in this course. We'll pick up that thread again before proceeding into using some advanced features of scikit-learn. The general workflow of fitting any model in scikit-learn starts by instantiating an empty model object. We saw in the case of linear regression that an empty linear regression object was created using the command linear_model dot linear regression and followed by parenthesis. It is recommended that you put all your features in one variable, say x, and your response in a variable called y. The name of these variables might change, but the workflow remains unchanged. Finally, once you have fitted the model, use the predict method to get the predictions for the new set of data points, which you can store in another variable, say new x. No matter what kind of model you want to fit, this basic structures of the code does not change. You might want to get the performance metrics out somewhere in between. Plot the result sets somewhere, but the structure remains unchanged again. So here is an example of fitting a classifier called support vector classifier in scikit-learn. And if you notice, how many of the variables have changed, but the basic structure we talked about does not really change. This way of interacting with Python library is a bit different from the other libraries. It is certainly a bit different from using list or writing a function or even using the NumPy or Panda libraries in Python. But with the practice, this will become easier and you will realize that scikit-learn has a very intuitive design. It just takes some getting used to it. So you will realize you can work with virtually any machine learning algorithms without really knowing the underlying mathematics of it. Let us now get back to our credit card default dataset. Remember, the first step in our workflow is to split the data into three parts: the train, test, and validate. The variables numTrain and numTest store the size of the training split and the testing split. In this case, we have chosen the splits to be in the proportion of 70, 20, and 10. But feel free to work with any other numbers if you wish to. Based on the credit data, numTrain is 20,720 and numTest is around 5,920. So the training split should be about 20,720 observations. The testing split should be around 5,920 observations, and the rest will go to the validation split. Before splitting, we use the method random.shuffle from the NumPy library. This rearranges the rows of the data in a random order. We have given an example of how random.shuffle works in the NumPy array. Now, feel free to go back to the notebook on NumPy and understand it better if you have to. Once the credit data is shuffled randomly, take the first 20,720 rows and put it in a variable train data. Take the next 5,920 rows in randomly shuffled data and put it into a variable test data. Put the remaining observations into validate data. Note that the last 3 lines of the Python code rely indexing in the pandas data frame. If you think you should have a look at how indexing works, please visit back the data frames that we discussed in the previous point of time in pandas. So if you have a look at it, there are 3 kind of variables that you need to keep track while working with machine learning algorithms. The numeric variables, which are essentially continuous real numbers, categorical variables, which are basically categories but can also be encoded by numbers, and response variables, which we have seen can be either continuous or categorical. In the Python script, we have 3 variables to keep track of these variables. The response variable is basically a string which stores the name of the column in the credit dataset, which stores the information whether the customer defaulted the payment or not. And the factor variable, which is factor vars, is manually created list which stores the categorical variables in the credit data like sex, education, marriage, and the status of the payment from the last 6 months. All these are categorical variables. So factor var is a list with 9 elements. All other variables are put inside a list named as numeric var. Now most machine learning algorithms are sensitive to type of input data. For example, to get the best result out of the algorithm, it is recommended that you standardize your numerical variables and then work with them. Categorical variables also need to be processed. Now, the way you deal with categorical variables to work with them with the machine learning algorithm is a bit different. Let's talk about variable standardization for the numerical variables. At the beginning, we had originally split the dataset into 3 sections: the train, test, and validate. The idea was to train all models on the train split, compare models on the test split, and make final selection using these results. Finally, we report the performance of the selected model on the validate split. Variable standardization, as noted earlier, helps you to get rid of the units in the numerical measurements in the data. For example, let's say you have 2 variables x1 and x2, and x1 varies from minus 1 million to plus 1 million, where x2, if it varies from 0.5 to 1.5. The drastic difference in the scale of these 2 variables will have a lot of impact on the final results of many machine learning algorithms. It can be either supervised or unsupervised. To bring these variables on the same scale, variable standardization is the weapon of choice. The idea is to calculate the mean and the standard deviation of each variable using the training set and store them away. You will obviously use this mean and standard deviation to standardize the training data. Also, use the mean and standard deviation when you want to standardize the testing and the validation split as well. Now, if you ask me why, the logic is variable standardization can also be thought of as a machine learning algorithm itself. And like every machine learning algorithm, it has to work with unseen data. But mean and standard deviation will not be available for data that the computer has not seen yet. Hence, whenever presented with a new data point, the computer will use its best guess of mean and standard deviation to standardize the new point. And where does this best guess come from? The data in the training split. So, if you see here is an example that will hopefully make the process clear. Let's say you have only one feature with 5 data points, 10, 20, 25, 40, and 50. Let's split the data into 2 random parts, which is 10, 20, 40, and 50, while the test split gets only one observation, which would be, I believe it's 25. You can compute the mean and standard deviation on the training split using a simple NumPy operation, which would be like the mean turns out to be 30 and the standard deviation is 15.8. Now, how do you standardize the train split? Simple. From each observation, subtract 30 and divide the results by 15.8 to get the array of standardized feature. Now the standardized training set has given you the output. Now comes the testing split. Here, you do not recalculate the mean and the standard deviation of the feature. You use the mean and the standard deviation that is already calculated from the training split to standardize the new data point. Thus, the raw data point for 25 gets a standardized value of minus 0.31 based on 30 as the mean and 15.8 as a standard deviation. Now that you have seen an example of how to do variable standardization, let's take a look at the piece of Python code which performs the variable standardization in a way that is useful in machine learning. Now, recall that we had seen variable standardization using the pandas operations earlier. We used an anonymous function inside a lambda operator on each numerical column of the data frame. We will now see how to do the variable standardization the Python way. And to do this, import the pre-processing module from sklearn. Trainx stores the numeric columns from the training split as a numpy array. Then you call the standard scalar method from the pre-processing and instantiate an empty standard scalar object called scalar. Use the method fit on the scalar object with the trainx as the argument. This calculates the mean and the standard deviation of each column in the data frame. The mean and the standard deviation can be accessed from the scalar object using the methods mean scalar dot mean underscore and scalar dot scale underscore. Note that the object scalar now contains all the informations you need about standardizing the numpy variables and the credit card data. Use the transform method from the scalar object to get the standardized value for each data point on the training split. Store them in a variable trainx underscore standard std. Notice that the standardization does not alter the number of rows or the columns in the data. It adds no new columns or deletes any column. It simply transforms each measurement in the data based on the parameters in the fitted scalar object. You should also note that in the transform method, if you change the argument from trainx to specify the numerical variable from the testing split, you should get back the standardized value for the testing split. There will be no need to recalculate the mean and the standard deviation as we have mentioned before. The mean and the standard deviation from the training split are now stored in the scalar object. You can use transform method on both the testing split and the validate split to standardize them.